Hello, everyone. Welcome to SETI Live. I am your host, Beth Johnson, Communications Specialist here at the SETI Institute. Thank you to our viewers from around the world for joining us. Please let us know where you are watching from. And also welcome into listeners on the podcast version of SETI Live, which is available on most podcast platforms. Launched on September 8th, 2016, the Origins Spectral Interpretation, Resource Identification, and Security-Regolith Explorer, or OSIRIS-REx, spacecraft traveled to a near-Earth asteroid named Bennu and collected a largish sample of rocks and dust from the surface. The spacecraft flew by Earth on September 24th of this year, delivering the capsule containing the sample, which landed at the Department of Defense's Utah Test and Training Range. Yesterday, NASA revealed the contents of the capsule live, and today I have the pleasure of being joined by OSIRIS-REx's principal investigator, Dante Loretta. Please join me in welcoming Dante to the live stream. Thank you for being here today, and of course, welcome.
Thank you. It's great to be here.
I'm so happy to have you here. So before we begin, I was asked to read a message to you from our president and CEO, Bill Diamond, who unfortunately was unable to drop by in today's stream due to his own travel plans. So let me just read this to you from him. Hello, Dante. I wish to extend my personal congratulations to you and everyone on the OSIRIS-REx team for an extraordinarily successful mission. I am on my way back to the Bay Area following travels up north, and as such, unable to join you live today. But I was Jim Green's guest at the launch back in 2016, and it was thrilling to be there to witness OSIRIS-REx lift off the pad and take to the skies on its way to Bennu. A truly historic mission that will surely offer unprecedented insights into the very origins of our solar system and potentially to the origins of life itself. Thank you for being with us today and spending time with our global SETI Live audience. OSIRIS-REx may be a mission whose acronym few can recite, but it's also a mission that people in the world may never forget. All the best, Bill.
That's very nice.
So obviously everybody's very excited for you, for the team. Let's we'll backtrack a little bit in case there are people who are not familiar with OSIRIS-REx. What is the OSIRIS-REx mission? What are its goals? And I gave sort of the background of its launch and all of that, but what are the goals of the mission?
OSIRIS-REx is a mission in NASA's New Frontiers program, which funds intermediate size and bold missions of planetary exploration. We're the third mission in that program. The first one was New Horizons, which flew by Pluto, and then the Kuiper Belt object Arrokoth. Number 2 was Juno, which is still orbiting Jupiter and probing the interior structure of that planet. And we're OSIRIS-REx, the third mission in New Frontiers. Our goal was to launch a spacecraft off the surface of the Earth, rendezvous with a near-Earth asteroid named Bennu, survey that asteroid in great detail, select a location on the surface to send the spacecraft down to make brief contact, what we call a touch and go or tag maneuver, scoop up as much sample as we could, and then bring that back to the Earth for investigation in our laboratories.
And so why Bennu? Why select that particular asteroid?
When we were first formulating the OSIRIS-REx mission concept, we knew we wanted to go after an object that held the most volatile compounds. When we say volatiles in the terms of solar system chemistry, we're talking about water, which forms ices and is abundant in the outer solar system, but is generally rare in the inner solar system, and carbon primarily in the form of organic molecules. We're interested in these objects because these compounds are stable in the outer regions of our planetary system, yet the Earth requires them to be a habitable world and for life and for our biosphere. So we were looking for the kinds of objects that may have delivered these crucial compounds to our planet. So composition and chemistry were really driving where we wanted to go. But we had to lay in some engineering constraints, right? At first we were thinking, let's go out into the way far asteroid belt and get this kind of material where it resides and bring it back. But that was going to take multiple decades to implement. We're like, well, we're not that patient. So we said, let's see what we can find in the near Earth population, right? There's this whole group of small asteroids and comets that are tumbling into the inner solar system from the main asteroid belt and from the Kuiper Belt and farther out in the solar system. And they're in an unstable configuration. They're not going to last more than maybe 10 million years before they collide with a planet or more likely fall into the sun. But they're much more accessible. And so we were looking for something in generally an Earth-like orbit didn't get too close to the sun where it would be too hot, didn't get too far away from the sun where our solar arrays wouldn't be that effective. And it couldn't be inclined at a really high angle relative to the Earth's orbit, because that would mean you're coming in so fast, there's no capsule that could survive that kind of entry into the Earth's atmosphere. And then we wanted something relatively large. There's a lot of small bodies, like 10 meters and so on. The smaller you go, the more abundant these things are in the solar system. But that was way too small for our sampling strategy. We wanted something that was going to have loose gravel-like material on the surface. And Bennu kind of checked all of those engineering constraints. And of course, it is dark. It's a really dark asteroid, reflecting like 4% of the sunlight that hits its surface. And that was our main clue, that it probably had a lot of carbon. Carbon is a good kind of atom, and carbon-bearing compounds tend to be very dark. And so that was what led us to pick Bennu as the target of OSIRIS-REx.
Fantastic. So you got there, everything went great. You did the touch and go, which was had a surprising result. Just to revisit that really quickly, it was not the boop you were expecting, was it?
That's right. So when we had done all of our analyses and all of our simulations, we expected that there would be cohesion among the grains, right? Even though we knew we're in a microgravity environment, we thought certainly something's holding this asteroid together, and there must be some kind of chemical bond, even a van der Waals bond, which is a very weak kind of chemical bond that's holding this together. And so all of the simulations where we had that cohesion property included, we didn't go into the surface more than just a few centimeters. But that's not how Bennu's surface reacted at all. We plunged deep into the asteroid. And the only models that made sense was that there was essentially no cohesion among the grains. And it's behaving kind of like a fluid, like hitting a pool of water or quicksand, more accurately.
And so when you say you plunged into it, was what, about half a meter, right?
That's right. Yeah, we estimate almost 50 centimeters into the subsurface. When we were expecting to go this deep, we went, the whole forearm of our robotic arm went down into Bennu. And we actually think that's good news, because the surface of Bennu tends to get really warm, but the skin depth, how far that heat sinks in, is only a couple centimeters deep. So we got some pretty cold stuff. And when you're looking for water and carbon and things like that, they're more likely to be preserved at those depths. So it was kind of a really nice Bennu surprise.
All right, I want to talk more about the sample itself, because obviously that's the big deal right now. But I'm going to welcome in some viewers first. We have people watching from around the U.S., so New Jersey, Illinois, Nevada, Arkansas. We also have people watching from Canada, the UK, Latvia, Norway, someone watching from Hawaii. Welcome in, everybody. Thank you for joining us. And once again, I am talking to the principal investigator of the OSIRIS-REx mission, Dante Loretta. We're going to talk some more about this sample. So part of the thing that happened with diving in so deep as you did was that your sample capsule doth runneth over. You had trouble getting it closed, if I remember correctly, but it's here now. And so yesterday we had the press conference. We kind of like showed some of what was on the outside, which was a lot. And so what have you found from that capsule landing so far?
Yeah, so what we needed to do, once the capsule was on the ground in Utah, we very quickly got it into a clean room right nearby the landing site in Utah, packaged it up and delivered it to where I am right now. I'm at NASA Johnson Space Center. I've been on site here almost continuously since the sample arrived. And we got it into the laboratory at JSC, where it's custom built for OSIRIS-REx. There's 2 beautiful glove boxes. We really want to avoid exposing the sample to the air on Earth. Oxygen and water, we think, could really react with the minerals that were stable on the surface of Bennu. Sometimes you can't avoid it. To get into an instrument, it's got to come out, get into air, and get into instrument. But we minimize that as much as possible, and most of the sample remains pristine. So that's great for the sample, but it provides a challenge for the processors, right? Because you have to get into full bunny suit, clean room gear. I've been in a few times. I go in for some key observations. It's hot, uncomfortable. I spend about an hour in there and I'm ready to get out. I'm just like sweating and I just feel like exhausted. So it's hard work. And I want people to appreciate how hard this team is working here at Johnson Space Center to do this. And then they got to go into a glove box. So you've got these big rubber gloves that push out because the cabinet is under pressure, dry nitrogen gas. and they got to push in, and they can only work, they got these holes where their shoulders fit. So they're really constrained inside there. So it's painstaking, delicate work of prime importance, and it's under challenging conditions. When we opened up the canister, I don't know, can I share something? Because I can show some of the pictures. Let me see.
Yeah, you absolutely can. So if you click down on the present button, it'll be there.
Yeah, let's take a look here.
And then I can add them to the stream once you have them. While you do that, I'm going to welcome in a few more people here. Let's see. We have someone watching from Florida, Ireland, South Africa, France. Wow. Welcome in to France from France. That's awesome. Bienvenue. Let's see. And of course, welcome to our Twitch audience, which is growing every day. Thank you so much for watching us on Twitch. And
okay, can you see my screen?
No, not yet.
Let's try again here. It said I was sharing, but let's try. Share screen. Now? No?
No, it doesn't like it for some reason. That's very strange.
Sorry. One more time.
Oh, Denmark, Virginia. Coming in from all over the Minnesota. I almost missed the Minnesota one.
I don't know what I need to do. I apologize. I don't know if you have access to the slides, the pictures that we showed at the press conference yesterday. That's what I'm trying to bring up.
If you shoot them to me in my email really quickly, do you have that? Then I can bring them up in just a moment.
They're really big files.
Okay.
Anyways, let's just keep going. You can find them there on images.nasa.gov and on Goddard Space Flight Center Science Visualization Studio, so viewers can go take a look at them. So the first thing we saw when we opened up the canister, so you got to remember this capsule's kind of like a nested doll. So you got the heat shield in the back shell that protects everything from the fiery passage through the Earth's atmosphere. Their job is done. They were pulled off. They're off at the engineering organization, Lockheed Martin, just evaluating their performance. And then inside there is the canister, which holds the TAG-SAM, the touch and go sample acquisition mechanism, with the actual device that touched the surface of Bennu, where most of the sample is stored. But when we opened the canister, we saw that there was all of this black asteroid dust kind of in the outer edges of that chamber. And it looked like what happened, since we had nitrogen gas flowing almost immediately, it kind of blew all the fine particles to the outer perimeter there. And there was so much material, over 1 gram of material, that we spent our time carefully collecting it, documenting it, cataloging it, and allocating some of it to my Quick Look science team. And they got to work on it right away. And a lot of the results that I showed yesterday were focused on that. Kind of the highlights are the water-bearing clay minerals. This looks like a picture from when we're still in Utah, what I see on the screen right there. It's processing it.
Let's see. There's where it's coming in.
Yeah, sorry.
Oh, no problem. I mean, they're there for people to look at.
They are. We've got a lot of carbon. Just the first fragments of asteroid sample that we measured are about 4.7% by weight carbon, one of the richest samples in carbon of any meteorite that we've ever analyzed. Maybe the most rich in carbon. We're still working through all the details on that. So the bottom line is we brought exactly the kind of material that we were hoping to collect back to the surface of the Earth. But that has slowed us down a little bit because we had so much material we had to process. Our procedure is a step-by-step, approach to make sure not only do we get our science done now, but we preserve the collection for future scientists decades from now that'll be able to access this material. And then we did get to the point where TAG-SAM came out of its capture ring. It was clicked in, I like to say, like a boot into your ski, right? We locked it in there so it was stable through the passage through the atmosphere. We pulled it off and we flipped it over, and we could see some of the material, not everything that's inside there, but some of the material actually had migrated on top of the flap, the thing that got stuck open when we were at Bennu that caused those particles to leak out. And it was beautiful. I spent hours and hours over the weekend just staring at the images, marveling at the diversity of what we see in there. And the thing I found most entertaining was when you zoom in and you can't see the spacecraft hardware anymore, it looks like the surface of Bennu. It looks like, I was shrunk down to this size and I'm running around on a mini Bennu surface. And it's amazing. So there's this scaling property. It seems like the morphology of the boulders on Bennu, some of them have very sharp fracture planes. Some of our kind of hummocky cauliflower-like texture. We're seeing those same things in the samples, and these particles are only a centimeter or two across right now. So if that is all we brought back, we would be super excited. We would be absolutely busy for the next decades. But that's still just a tease of what is inside. We've taken flashlights, as you can imagine. We go in there and we can shine through, and we can see some big stones inside TAGSAM. So the volume of material looks substantial. I'm hoping by next week we start to get our first glimpses inside that. So it's slow going. I've been practicing my patience as best as I can, because nobody wants to see inside there more than I do. I guarantee you that. But I understand the need to do this carefully, cautiously, and that's kind of been the hallmark of our mission all along.
Right. So it's taken what so far, you spent 10 days unraveling this, trying to get into the TAGSAM, and you're still just on the outside.
Yeah,
So
I can see the feed. I'm looking at the processors in the clean room right here. They're starting to pull off the contact pads. So in addition to the bulk sample collector, there was 24 pads of stainless steel Velcro around the outer edge of the base plate, the part that touched Bennu. And those hopefully have some surface material, because we want to do the spectral characteristics. How does the light interact with the very surface? And
so these are the circles right around the edge.
Yeah, where we saw some of the particles that escaped outside of TAGSAM. So the contact pads are those kind of dark discs that are dispersed all around the outer perimeter there. So we've pulled off that bottom plate now, and we're starting to carefully extract each one of those contact pads. There's some of them that look like they have particles associated with them. So we're targeting those first, macroscopic particles, millimeter size things. And those are a very special collection, because those are, as I said, the optically active surface of the asteroid. So we went deep, but the contact pads should have grabbed the very first thing they touched. So there's 24 of them, and each one of them needs to be handled delicately, put into its own little special container, photo documented and cataloged. And that's where we are right now. So we're a little bit farther than this picture shows you, but kind of still dealing with the surface layer, the stuff that actually touched Bennu. The next thing that we're going to do is you can see 6 bolts on the inner nose cone there. We're going to pull that off, and that flap is going to come off. And then we should start to see really what's going on inside the full sample collection chamber.
Do you have a time estimate on how long the next part of this process is going to take?
As long as it takes. So we update the schedule every day, right, based on how far we got in our procedure. I'm optimistic we're going to see inside TAGSAM next week, unless there's some new surprises as we get deeper into the hardware. But the plan is by next week we'll have eyes on the bulk sample.
That is incredibly exciting. So something that maybe people aren't aware of, one of the great things about this mission was there was a sizable portion of citizen science that was involved in selecting this sample site. I am one of the people who marked boulders and rocks and craters and more rocks and some more rocks. Bennu was definitely a lot rockier than we expected.
That's right.
So how did that affect where you chose to do your sample? You had like a few selection sites possible. So how did the citizen scientists help with that selection process?
Yeah, it's one of the reasons why we explore, right? So when we were working on the mission concept, starting as far back as 2005, we had kind of zeroed in on Bennu as our target, even way back then. And in 2005, Bennu was doing a very close approach to the Earth, which it does about every 6 years or so. And so we ramped up this huge astronomical campaign, and Bennu became the best telescopically characterized asteroid in the solar system. And we were really trying to figure out some fundamental properties to inform the spacecraft design, right? Like the engineers were like, what can you tell us about this asteroid? And we're like, well, it's a point of light in the sky in the telescope. But we did better than that. We had radar data from Arecibo and Goldstone planetary radar systems, and we mapped the surface to about 7.5 meter pixel scale, which was phenomenal. And we got the shape of the asteroid. It's got that really cool spherical kind of spinning top shape. And the radar data, both Arecibo and Goldstone, which use different wavelengths, one about 3 centimeters, one at about 12 centimeters, it looked really smooth. at those wavelengths, which suggested that the radar roughness, kind of the wavelength of the surface, was smaller than 3 centimeters. And then confirming that hypothesis was the Spitzer Space Telescope data. Spitzer is one of NASA's great observatories. It uses infrared wavelengths to study thermal properties and mineral properties of protoplanetary disks and all kinds of great astronomical objects. We also used it to study Bennu, and by watching Bennu rotate in front of Spitzer, you could see how quickly the surface heated up and cooled off, kind of its thermal, what we call thermal inertia, the resistance to change in temperature. And Bennu heats up and cools off really quickly. And typically, a low thermal inertia like that means small grain sizes, like sand on Earth tends to heat up and cool off really quickly. So we said, oh, the radar surface is smooth, the thermal inertia is low, it's got this spinning top shape, which means that material's moving around and kind of equilibrating. We thought the average particle size was going to be centimeter scale based on all of that information. And then we got the first pictures of Bennu in 2018 when we were on our approach phase, and we're like, where's the beach, right? It's like, this is nothing but rough and rugged boulders. And, you know, we would get a new data set every week when we were doing our detailed survey phase in 2019. And I would stay up all night as the images were coming in and just going frame after frame, and like, there's nowhere to sample on this asteroid. It's like, it's just a rugged boulder field everywhere. But there was so much data that we needed help, right? It was like, we're getting all of these really high resolution images. We were realizing we're going to have to find an area maybe 10 meters across before we thought we could target something as big as 50 meters. So we needed a 20% of our guidance accuracy over what we had originally launched with. So the team was put to work, everybody on the team. I don't care if you were in accounting or graphic arts, you were looking at pictures of Bennu and trying to find sample sites for us. And even then we said, you know, we need more help. So let's go to CosmoQuest. Let's get our citizen scientists out there. Thank you, Beth. Thank you to all of our Bennu mappers. You guys got a sample site all the way to the final 4. One of the CosmoQuest sites was the Kingfisher site, which made it to almost to the championship. In the end, we picked a site called Nightingale, which turned out to be a fabulous location for collecting a sample.
And now we have that sample here. And so I'm going to take audience questions because we're getting close to the end of our time. So if you have questions for Dante about OSIRIS-REx, please feel free to put them in the comments. I do have someone behind the scenes marking them for me so that I can find them. What for you? So basically, I would normally ask you what is next, but clearly what is next is still just extracting this sample from within the tag capsule. So what have we learned so far? You mentioned that we've done some minor analysis on the particles we found on the outside. So what have we learned so far, and what do you think that can tell us as we go further?
Yeah, so but just to say what is next, we have a whole sample analysis plan, right? So we've got over 220 scientists all around the world getting ready to receive this material. So yes, getting inside TAGSAM is the absolute next step. But the reason we want to do that is because we can allocate up to 25% of that material to my science team, which is all over the world. And if the listeners are interested, I posted the sample analysis plan on archive.org. So if you just go and you search OSIRIS-REx sample analysis plan, you'll pull down that document and you'll see everything we've got in store. So really what happens once we get TAGSAM open, the agreement with NASA is 25% goes to the science team, 75% goes to the international partners and into long-term storage for future researchers. And when we wrote all of that down, I think back in 2008, what we didn't describe is how do you pick the 25% that goes to the science team? Because, you know, the scenario that we always envision would be you have this big pile of black asteroid dirt, and then there's like this blue marble that's sitting in the middle. Everybody's like, we want that. And it's like, you know, you can't go for the shiny thing. You kind of got to go characterize the nature of the collection. So we went through a lot of, you know, we have these activities we call SOPIEs, SOPIE, Science Operational Proficiency Integrated Exercises, where you practice decision making. We had simulants. We went through with the curation team, the photo documentation team, the science team, and it said, okay, what information can you extract about the sample while it's in the glove box, while it's curation pristine, before we do anything that might compromise the integrity of the material? Spectral imaging is a big part of it. We have a multi-wavelength broadband imaging system we call CRIS, the quantitative reflectance imaging system. We have a pycnometer, which we have installed. A pycnometer is a device that measures the grain density and the porosity of particles. And that it uses the curation nitrogen. So it's a beautiful way to do that. Obviously, we have a balance that we can measure the mass of individual particles as they come off. We have a structured light 3D scanner, so we can build three-dimensional shapes of the particles. You get the mass, you get the bulk density, you put it in the pycnometer, you get the grain density. And what we agreed to is, I don't want to compromise the collection in any way. I don't want to take more than 25% of any kind of material that's in there. Right. So we agreed on the rule of 4. If we think we have a certain kind of rock, and we think there's going to be multiple rocks, we need to find 4 of them and convince ourselves with that suite of information that they are, in fact, the same rock type. And then I get to pick one of those that amounts to 25% or less of the combined mass of the 4. So that's what's going to start happening after next week. Once we get TagSam open, we'll be doing extensive characterization and trying to identify the different rock types and picking the ones that are going to get out to the team all around the world.
So what you're saying is you're moving to Houston for a while.
I'm commuting to Houston. Yeah, I go home to Tucson on the weekends right now.
Wow. That is a commute. So anybody who complains about their commute, remember, you don't have to change states that far. That's a lot. Yep. Okay, so we do have some audience questions coming in, and I see that people are asking about the weight of the sample.
It's coming.
I promised I wouldn't ask about it, so I'm not gonna ask you for the estimate.
Nobody wants to know that more than I do. Trust me.
I am sure. There is a really interesting question from Twitch, though, and it sounds like this came up yesterday, and so I'm happy to ask this one from Q23. Why did you not weigh the whole container and subtract its empty weight to determine the weight of the sample you received?
The whole container weighs about 50 kilograms, and we think the mass of the sample is about 250 grams. So we don't have a balance that's capable of discriminating 250 grams out of a 50 kilogram mass. So, and that just, that problem is getting smaller as we remove components, and it's getting to be less and less. The balance is about 5 kilograms now that's inside the glove box. And we're right at that limit. Like with the hardware that's on there, it's about 5 kilograms. And so we don't have the precision yet. We got to keep pulling stuff off until we get under that weight, and then we will get you a mass. So it's a precision issue.
That makes sense. Okay, let's see. Let's go here. If you were to do a similar voyage to take sample on a more metallic asteroid, would it be necessary to modify the OSIRIS-REx capsule, the collection arm, obviously? How much pressure could OSIRIS-REx take?
OSIRIS-REx could have contacted a solid surface, and that's kind of what we predicted. So the design of the robotic arm actually had a pogo stick-like spring on it. So we could hit a slab of concrete, and the stick would compress the spring, and then if nothing else happened, like the thrusters didn't fire, it would just pogo off the surface. But if you're trying to collect a slab of metal like an iron meteorite, and those can be huge, 60 tons is the biggest one that we know of on Earth, the TagSam wouldn't work for that. So you would have to come up with a way to fracture metal, which is really hard to do. So yeah, we would have to it would be a totally different sample collection strategy if we're going to a SETI, for example.
Right. And okay, this is another, I like this one. Kelly asks, what areas of OChem or advanced instrumentation are necessary for sample evaluation? You talked about that just from a basic, here's what we have to do to kind of figure out what we have. What else is going to, do you know of that's going to be done?
Yeah, so OSIRIS-REx samples look like an organic chemist's dream. So anything you can imagine that's used to characterize these kinds of compounds.
Uh-oh. Oh no, we've lost him. Of all days. Let's see. I do see other questions. I'm going to see if anybody has said anything while we wait for him to come back. I did see people coming in from, someone came in from Germany and someone came in from Peru. So welcome in, willkommen. Hello. Okay, let's add him again, and we'll take this off the stage. There we go.
All right, so we're talking about organic chemistry. So gas
Yep.
chromatography, mass spectroscopy, liquid chromatography, mass spectrography, Orbitrap, mass spec, pyrolysis, bulk carbon, hydrogen, nitrogen, oxygen, sulfur, phosphorus, isotopic characterization using secondary ion mass spectrometers and time of flight mass spectrometers, L2MS, laser desorption mass spectroscopy, spectroscopy, infrared spectroscopy, you name it, that we're going to do it, right? We've got over 60 different techniques that have been identified. Many of them are focused on the organic chemistry.
Fantastic. That is going to be, that is a lot. And this is going to provide research for years, if not a decade or more. So I'm going to finish this up because we're kind of at the end of our time here, and I don't want to not talk about this. OSIRIS-REx isn't done per se, right? The spacecraft itself is still out there. You're still in control of it. Tell everybody what is the next part of that mission, because I know, but let's tell them.
Right, and you're half right. So the spacecraft is still in outer space. It dropped off the capsule. I am no longer in charge of it. I have handed the reins of the mission over to a young early career professor at the Lunar and Planetary Laboratory, Professor Daniela Della Justina. She is now the principal investigator of a new mission called OSIRIS-APEX, which is the Apophis Explorer. Apophis is another very well-known near-Earth asteroid discovered in 2004. When it was first discovered, it looked like it might be hitting the Earth in 2029. We know that's not going to happen, but it's going to come real close to our planet, like within the orbit of our weather satellites. And it's about 300 meters in size. So it's the closest, biggest asteroid flyby for 1,000 years. People will be able to see it with the naked eye in Europe and Africa during its close approach in April of 2029. Very rare event that you can see a near-Earth asteroid without a telescope. And so the OSIRIS-REx spacecraft has been rebranded to OSIRIS-APEX, and it's going to rendezvous with Apophis in April of 2029. And that's just amazing. I knew we were looking for extended mission targets because we have this fantastic spacecraft, very capable. All the science instruments are still on there and functional. And I thought for sure we'd be doing a flyby, which is usually what you can find when you're just searching through the solar system for a target you can get to. And the flight dynamics team came back and said, we can put you into orbit around Apophis. And I was like, we got to do that. So yeah, it's a long cruise. It's like 5.5 years to get there. But what I'm most proud of is that everybody that's going to be leading that mission started out as an early career person on OSIRIS-REx, and we've trained them, and we're all handing over the reins to the next generation. And to me, the legacy of the sample, the data from Bennu, and the APEX mission is something that I'm the most proud of.
That is incredible. I am so excited for you, Dante. This has been a fantastic ride. I am glad that I have gotten to take it with you as much as I have. And definitely I'm going to want you back when we have results from various things. And then you will also let me know what other scientists to talk to when we have results, because I'm sure they will want to talk about their success too.
And if I can do a sneak preview, I'm giving the Eugene Shoemaker lecture at the American Geophysical Union. So that will be a grand unveiling of a lot of our greatest science results. And that's in mid-December.
And with luck, I will be there.
Awesome.
In person. So we will actually get to meet face to face, and I will definitely be interviewing you there.
That sounds good.
So thank you for joining us today. Thank you so much for being here. This has been a huge honor. I am so pleased for you. I can't even begin to express. And I'm excited for the OSIRIS-APEX portion of this. And I feel like these new frontier missions have really proven themselves beyond all sort of like expectation. I mean, all three of you have gone into these extended missions and continued to do amazing science. So I'm really happy for you, and congratulations again on the successful collection and return, and good luck in getting this open.
We'll get it open. No, it's because we have an abundance of riches that we're going slow. So it's all good news.
All good news. All right. Well, thank you again. And thank you everybody for watching us, for spending this last half an hour and some with the two of us to talk about this amazing mission. We are the SETI Institute. We are a 501c3 nonprofit, of course. And if you would like to support us, please go to seti.org/give now. And you can help keep us doing these outreach programs like this one and like our sci-fi reality check and all of these things that we do to bring you science. So thank you everybody for joining us, and make sure you like, share, subscribe, do all of the things so that other people can hear from Dante about this amazing mission and see more of the amazing science. Thank you everybody, and we will see you Saturday for our live eclipse stream early in the morning on Pacific time. Here's hoping that the various telescopes we have are not clouded out. So we'll see you then, and thank you again, everybody. Thank you, Dante.
Thank you.